Is all the screen sharing and everything working? Yeah. Okay, so I need the title, so I put non-smooth because I know this is very fashionable, but the talk is actually much broader than that. It's basically a summary of my ongoing MuJoCo project that's been going on for embarrassingly long. So I'll mostly talk about trajectory optimization, which has gotten very extensive, and I'll emphasize non-smoothness. I'll summarize applications, and I promise to release the software as a beta release in September. Those of you who are old enough might remember that I gave a talk at NeurIPS 2019, promising to release it in 2020, but this time's for real. One starts with sampling. How do I get rid of this stupid thing at the top? Is that even possible? Oh my God. Okay, so sampling is great. Just to introduce notation, given an initial state, sequence of controls ran through discrete time for dynamics, MuJoCo, status, position, and velocity. Get a trajectory. Trajectory cost is sum of some kind of step costs. It depends on states and controls, but the states are fully determined given controls, so just you. Find some control sequence perturbations, which let's say some Gaussian process. Evaluate each one of them. So let's say you want to optimize this function. Compute an advantage, to borrow the language of reinforcement learning. And notice that this advantage is basically a directional derivative if the noise is small enough. So once you do that, what you do with those samples, well, there are multiple ways to. Why is this not advancing? How do I get rid of all these things? Okay. You can pick the best sample, which is proving to be remarkably good in the context of model predictive control, and the MJ PC people from DeepMind found that, and I've been finding the same thing. But you can do other things. So you can do path integral inspired frameworks like MPPI, etc. And Ivan is going to talk about those. So here you weight the samples somehow. If you just weight them by the linear weights, so you can notice that this is unbiased approximation to the stochastic gradient approximation. And policy gradient is just that, but multiplying by the policy Jacobian. So the success of sampling kind of introduces an elephant in every optimization workshop. And it raises the question, is that all we need? I mean, do we still need all the math that we do here? Or are we done? And I think we're not done, but sampling definitely raises the bar for analytical methods. Like if you can't beat sampling, join sampling, basically. If you can beat sampling and you can develop an analytical method that actually does work better, you can still use sampling because the best analytical methods will always get stuck. Sampling doesn't get stuck. So you can revert, you can fall back automatically to sampling, and you can get hybrid methods that combine the efficiency. And to me, this is the default now. Like everyone doing analytical methods should have a well-tuned sampler in the background ready to take over. Now let's have some fun with sampling. This is joint work with my daughter, Emo Todorov, who is into soft robotics. So our so-called robots are actually cubes. We want them to walk, in quotes. So simplest possible cost, center of mass has to reach a goal, a Hilbert distance because those are nice, control squared, that's it. So we don't mess around with shape rewards. The three robots, all of them are kind of flexible things. There's a core body in the middle, which has 6 degrees of freedom. And then the vertices have 3 degrees of freedom relative to that core body, and those can be actuated. So here we have 30 degrees of freedom, 24 controls. Here everything is actuated. In this big one, only the 8 columns are actuated. Time step is 10 milliseconds. MPC horizons. Turns out longer MPC horizons do help. This curry thing runs in real time. These flex boxes are about 3 times slower than real time on a really good thread ripple. Now, much to my surprise, turns out using half the thread ripple is kind of the sweet spot. Why? Because you give half the samples, but you allow the thing to boost its clock, and you evaluate those samples about maybe 20 to 30% faster. Adding samples, like you hit the diminishing returns regime very quickly. And I didn't know that when I bought that thread ripple, but now I know. Okay, so let's see these things in action. This is, I gave up on a live demo because of this screen sharing, so I pre-recorded, but I promise you this is running in real time on my laptop. So this thing is happily chasing its target on a laptop. So, it's a good processor, but still. Notice what it does here. So the center of mass has to go to the target. So it figures it should put its belly on the target and then calm down. And that's the game. Horizon is 100 steps to 1 second, so it can kind of see through that. It will, like, sometimes it puts a leg on the target and climbs up. Now I'm going to be evil and turn the target so that it cannot really set flat on it. And it becomes more difficult, but it kind of does. And so on. Now let's look at those crazy things. So this guy turns into a pancake ninja and navigates those obstacles and gets somewhere close to the target. Here's that guy in a more friendly landscape, so he just kind of squeezes through that.
This is also live?
No, this is 3 times slower than real time on a Threadripper. That has no chance. Okay, here our secret plan was to get climbing stairs. See what it did. It saw that it can just jump to it and landed there, and that's it. This is horizon of 200. This is how the big ones walk. So it's not real time now, but in a few years from now, it will be. Pretty cool. So sampling, not bad at all. Now, there are much more problems with sampling. One of them that I've kind of been thinking about is this. So suppose you generate random control perturbations, then let's say the variance over time is order 1. Now, when you integrate them, you get velocities, you get order t, like so it grows linearly in time. And then positions grow not quadratically, but cubically in time. Why? Because you integrate once already once, and you introduce very long time correlations. And so as a result of that, the tail end of the trajectory jumps around like crazy. And you're basically not doing local search at that point, which is why shooting methods with sampling tend to be limited to short horizons. So I figured out a way to solve this. And the solution is baked into a cube. So here's the idea. The user specifies the stage for noise generation, and the stage could be position, velocity, or control. So we generate white noise at that stage. Then we smooth it. This is like a minimum snap penalty, and we can enforce equality constraints for like fixed initial states and such. And then if the algorithm needs noise at a different stage, let's say shooting needs control, direct methods needs position, we will differentiate or integrate together. And that way we can actually control how this thing goes. Now, it's not exactly a free lunch. So let's say this is the power spectrum of the smoothed noise. This looks a lot like a Butterworth fourth order filter because it actually is. Like minimum snap smoothing of white noise is equivalent to fourth order Butterworth filter. Surprisingly similar. When you differentiate, you're multiplying by frequency squared. So you end up with this bandpass filtered noise. So if you look at the controls that you get from this procedure, they kind of bring it. They tend to have some the frequency. It's not ideal, but you get longer horizon. So that's a nice trick. It could be used outside to keep if anyone feels like implementing it like the entry lab people do, I guess. All right, now let's do a bit of math. So this is something I'm very excited about. Direct methods, which I'll explain in a moment, can, they optimize positions and they do wishful thinking in feasible trajectories, but they can do long horizon planning. Shooting methods are guaranteed to give a feasible trajectory, but so how do we bridge the gap between those two? So I found a really nice way to bridge that gap without any magic and keeping your fingers crossed. So I'll explain to you how it works. Just at the top, this is how MuJoCo physics works. So there's this extended Gauss cost for the extended Gauss principle. So this is mass times acceleration plus whatever centripetal, whatever. This is the usual Gauss term. And we add a penalty for constraint violations. That's where the stop constraints come from. For dynamics in MuJoCo is defined as the argmin of this Gauss cost minus the dot product of acceleration and force. This is a convex C1 function. This is convex quadratic. So there's a unique global minimum. The MuJoCo is always really good at finding it with Newton, Leibniz, etc. So since it's a unique global minimum, the gradient is 0 is the solution, which gives us the inverse dynamics. So the inverse dynamics is simply the gradient of that Gauss cost. Now, in a direct method, we want the actuation forces to be able to explain the kinematics, right? So we want the actuation force, which is this. So these are controls U, they're mapped to forces through something that depends on the state. We want the two to be the same, so we're going to define the discrepancy. We're going to call it the magic, which is typical in like continuation methods, like wishful thinking. Now, let's look at the direct problem. So we're going to augment our task cost with the discrepancy between those two things. Ideally, it will be 0 for a strictly feasible trajectory. This mu should be big. Now, MuJoCo imposes a specific cost structure. You can do whatever you want in the state, but the control is quadratic. Why? Because there are all kinds of low-level solvers to basically deal with the controls and focus on everything else. And it's not particularly restrictive. Like, you probably want that anyway. Now, the controls can be optimized away given the positions, velocities, and accelerations. This is the quadratic. We can impose box constraints. So it's either box constraints or analytical formula. And then at the end, the decision variables is only the sequence of position. So given those, you find a difference, get velocities, accelerations, get the controls through this, you have your augmented cost through that. Okay, I've talked about this before. Now the new thing is here. So now I'm going to design a relaxed shooting method, which sees exactly the same trajectory cost as the direct method when you give it an infeasible trajectory. So here's how it works. I'm going to keep the state space the same, the dynamics are the same, driven by applied force. But now I have an augmented extended control model, which just says original controls plus the magic forces are now allowed to be controlled. Then the augmented actuation is the sum of those two. Think of alpha as being one. We get an augmented cost, which is the old one, plus we put a quadratic penalty of these magic forces. And now you can see that when the magic forces satisfy this thing, this relaxed shooting method and the direct method see exactly the same. So now we can do a handover from direct to shooting without any gap, without nothing changing. Just change to a problem formulation that has a different set of decision variables, but it's guaranteed to have the same cost. And now, so at alpha equals 1, these two agree. When you bring alpha towards 0, now here's the clever game I'm playing. I'm tuning down the effect of the magic force, but they're still penalized fully. So when you set alpha to 0, you're still paying a price for magic forces, but they don't do anything, so you might as well set them to 0. So this gives you a perfectly smooth continuation path from wishful thinking to feasible. There are no infinite ways, there are no log barriers that have to become infinite, no mental graduations, no SQPs with merit functions are always ad hoc. This relates to multiple shooting sort of. Multiple shooting is another way to bridge this gap, but it kind of has the flavor of these merit functions that you're mixing apples and oranges. So you can think of multiple shooting having shooting segments of 1, meaning not shooting at all. And then the gaps between them, they're guaranteed to go to 0. So this is nice, it's implemented, very pleasant. Now I'm going to go to a much higher level of description and summarize the whole space of trajectory optimizers in MuJoCo, because I think it's pretty clear by now, there's no one method that dominates everything else uniformly. You need all of the above. And since the space, it has axes. The first axis is what I just talked about. Direct, this shooting, relaxed, continuation. The red things are kind of unusual, novel things I'm talking about. Another axis is whether you do sampling with this variant shaping I talked about, or the hybrid that I glossed over, or Gauss-Newton with no smooth provisions, which I talked about. Now in that space, we can have multiple algorithms. MPC demo I showed you is down here. And the sampling can extend throughout the whole axis. I'm going to talk briefly about these two algorithms. This is called inverse direct dredge-up. It targets the direct relaxed formulation with the Gauss-Newton. This is a successor to iterative LQR, and I'll explain to you why. So this can target all the relaxed, the shooting methods from strict to relaxed. And so basically the way I envision this being used is start with wishful thinking planning, hand over to shooting relaxed, clean up, execute with local feedback, because this thing will go to give feedback. Now there are other orthogonal axes in this space. There are all kinds of settings. In particular, one thing that's very nice is this remote contacts, which is a different form of relaxation. This is inspired by our contact environment optimization work with Igor Mordak many years ago. And now it's incorporated again into the program formulation. So this is another type of unusual control relaxation. So keep the state space the same, meaning any value functions you put over the state space can be reused, but just change the definition of what a control is and what the costs are. So before I get into details, let me address the implicit contact planning business. So in everything I'm doing here, contacts are implicit in the trajectory, fine, but still phenomenologically they're somehow discovered or planned. How does that happen? So sampling everything is an accident. Roll the dice enough times and eventually you may get lucky or go broke before that. Whichever comes first. This LQGD I'm going to describe, it optimizes contact modes of existing contacts, like meaning slip, break, stick. But new contacts emerge by accident in a forward path. Of course, same thing with LQR. IDT is different. It is designed to discover the utility of contacts that have been detected in MuJoCo has like marching gap thing where you can detect contacts that are nearby. Forces are not applied yet, but they're there in case somebody wants them. So now somebody wants them, finally, after 15 years of these things being there and maybe nobody ever using them. You've all just changed the convention on me. And so now the new MuJoCo doesn't work with my optical, so I have to change. He redefined what contact and gap means. So what happens when you sell your software. And then finally, these remote things, what they do is they discover utility of remote contacts from a distance, and then they encourage optimizer to reshape the trajectory to go make those contacts. So there are multiple ways in which contacts emerge. Now I'm just going to outline this algorithm. So IDT is just Gauss-Newton applied to a direct problem with non-smooth provisions. LQGD is generalized LQR applied to a shooting problem with non-smooth one-step solver. So I'll describe that in some detail. This equation here is key to optimal control. It just says the greedy policy is diagonal over control. So the control cost plus the value evaluated to the next step. When you're doing LQR tricks, value is quadratic, f is linear in U, this is quadratic. So, it's just get a linear feedback control, choose optimal, plug it in, you get the Riccati equations, propagate backward. Now we're going to change this picture as follows. We're going to still have a value function approximation that's quadratic, because unfortunately, that's the only thing we know how to compute in high dimensional spaces. So it's quadratic in the next state f, but the f now is piecewise affine in U. That happens when you have unilateral constraints. So let me explain that a little bit. So I'm rewriting this dynamics equation from earlier. So on the left, you have the applied force from your actuators. On the right, you have the output of inverse dynamics. So this is mass times acceleration, Coriolis, gravity, whatever. This means truncation. So this is negative, remains negative. It becomes positive, it gets truncated to 0. So this is like upper truncation. Now, if you had bilateral constraints, this truncation bracket would go away. Acceleration will just be folded. This J transport dj will just be folded into the mass matrix. And that's why bilateral constraints are really easy. It's like almost, you're not doing anything special, almost. Unilateral makes it even. You can think of the entire MuJoCo constraint solver as finding an A that satisfies this equation for a given U, except it's not solving it that way. It's reformulating this equivalent convex optimization problem, which solves very nice. But for the purposes of designing optimal control algorithms, we have to recognize that there's a piecewise affine relationship between controls and accelerations. So now, normally, iterative LQR would linearize around the U given by the forward pass and then build a quadratic. Now we're going to actually solve this thing, recognizing that this thing is piecewise linear and therefore it's a big mess. In particular, that mess is a mixed integer quadratic program with exponentially many pieces, just so you know what we're talking about. You have 10 simultaneous contacts. Each of them is a friction pyramid with 4 hyperplanes. That's 2 to the power of 40. That's roughly 1 trillion pieces. Now, heroic things like Gurobi can attempt to navigate those and give you a certificate of optimality. They run out of steam at about 30 something hyperplanes, which is like 7 contacts. And beyond that, it goes to other equity. They're very useful to see how good your approximate solvers are on small problems, but they're not useful. So that's the bad news. The good news is that I have a solver called this goal-directed dynamic solver, which handles this heuristically and finds very good solutions quickly. And so that's becoming the core of basically what I'm doing here. And then the forward pass is also modified. So now what I do in the forward pass is instead of relying on the linearized feedback gains from backward pass, which was specific to one of these piecewise affine pieces, when I do the forward pass, I'm now in a different piece, so I shouldn't trust those gains. So what I do is I run the GD solver again and just find the problem. IDT, this is a similar idea applied on a trajectory level. What changes? Well, actually, things get very complicated. So here, we are just playing with controls and accelerations. When you do a trajectory level, all these constants that are written as constants, they depend on all the positions, and now you have to extend this. I'll skip this. Just some old work. So this is my old GD solver. How quickly does it find solutions? So if you have like a humanoid or a hand, just run forward dynamics. This is how many microseconds it took 8 years ago. This goal-directed solver, which is solving this non-convex, non-smooth optimization problem, is within a factor of 2 basically. So it's super fast. There's also an old version of this IDT thing without non-smoothness, so this is the pre-pandemic MuJoCo, the one that I promised to release. It solved this acrobat in 30 milliseconds, and that's the trajectory. This hopper we initialize to just trajectory moving back and forth. We press run on the algorithm, it solves like 300 and some milliseconds, and this is the trajectory it finds. So locomotion things, you can handle by doing Gauss-Newton without any provisions for non-smoothness. Do backtracking, line searching, keeps your fingers. Locomotion has basically turned out to be an easy problem, and in retrospect, why is that? Because gravity makes sure that you make contact with the ground. Don't have a choice, really. Once you have that contact, you have the control authority to propel yourself forward by some kind of wiggling. And that's why RL finds it. That's why methods that are not designed to be non-smooth can kind of handle it. Once you go to things where, gravity, so basically gravity tells you which contacts to make. That's the hard part, and gravity solves that for you. Very nice of gravity to do so. Okay. These are these remote contact relaxations I talked about earlier. I'm running out of time. So basically, Igor's old work took about 5 to 10 minutes to generate these. You probably see not these videos, but these video clips. They're not consistent with any particular model of physics, but they're truly fascinating. I've now reformulated this as a different kind of control relaxation. So now I have a type of actuators built into MuJoCo that basically do what Igor did, and they come with very particular costs. And what they do essentially is they say, okay, I'm going to give you the control authority to push that microphone from a distance. But if you choose to use that control authority, you're going to pay control cost, and the control cost scales with the distance and the force. And so now if the optimizer chooses to engage those, it doesn't have to keep them to zero. If it chooses to engage them, why is that? That means because pushing that microphone did something in terms of the task. It was good, but it paid the price for being far away. And then the next iteration comes back, says, oh, I know how to minimize the price, just move closer to the microphone, right? So basically, we let the solver figure out that some contact would be nice to be there, and then we have a cost that says, okay, well, if we decided this is nice, how do you reduce the cost? We just go there. Right, so that's why we don't need this in locomotion, because gravity does that for you. In general, this kind of magical force interaction can do it. This is nice. So in physics inspired inverse kinematics. So what I'm doing is I'm defining IK as this thing on the second line. So you have a reference pose, Q bar. Q is my decision variable. What's the next pose? So I'm not integrating anything. This is solved as a well-defined optimization problem with monotonic, so nothing goes unstable. Stay close to the initial pose. This is like a weak, small weight, but it's a nice regularizer. Match a bunch of end effector targets, and most importantly, do not impose constraints. Use MuJoCo physics. So if you have a MuJoCo model, somebody already tuned all the constraints, and we already have a constraint panel. So this S hat here is very similar to the MuJoCo constraint penalty, except the constraint penalty depends on position, velocity, and acceleration. This is just position, so it cannot be the same. I have to hack it a little bit, but it's pretty nice. I'm just going to show you a little bit of me editing this thing. So you can do things like set constrain certain things. Like if they're becoming incompatible, it starts moving in funny ways. You can violate them, but then it quickly snaps back to what it's supposed to be. This is a nice, next thing is nice thing where you can kind of incorporate something like gravity in this formulation. So now these bodies, see what they're doing. I can move them around, and then when I let them go, they snap to the floor. So with this, you can really pose the model in all kinds of things. Now I'm going to kind of obstacle. This thing came back, evil. Okay, so now I can. This is called Natasha now. We finally painted the orange MuJoCo humanoid. Right, and we can extend this to path optimization, which I'm going to show. This rendering, by the way, you can get in MuJoCo with additive transparency. So here I'm going to drop a few pins and maybe some keyframes that don't have the time, so I'm going to advance to this. Okay, so when I'm done with that, my keyframes, I hit one key and this thing happens in like 5 milliseconds or so, and now I have some kind of happy trajectory going through this and minimizing constraints. Okay, so what's the point of all this trajectory optimization? Obviously, a good thing itself, but MuJoCo actually builds on top of that to solve much broader problems. One is obviously feedback control. My favorite at runtime is doing short horizon MPC using a learned state value function on the horizon as final cost. Why? Because MPC is myopic, especially when it's short horizon, but you can learn the value function offline and it summarizes the future for you. We did something called POLO, like plan online, learn offline, that's related. State estimation, you can use trajectory optimization for state estimation. I mean, to realize that, but instead of doing a recursive Bayesian estimator at the current time, you do it, let's say, 20 time steps in the past, and you bridge those 20 time steps with a trajectory optimizer, where all the sensor likelihoods, you turn them into costs, basically, and you minimize that in very stable variance. Motion retargeting is just a special case. System ID. System ID is really a joint optimization problem between trajectories and physics parameters. Because when you're doing system ID, you should not pretend that you know what trajectory is. Like you don't. In fact, that's kind of the whole point. If you have modeling errors, that means your trajectory is also wrong. Implicit grid reports is really nice. So this GD solver allows you to define policies by starting with the value function and then optimizing the actions in place. And it's almost as fast as the physics, so you might as well think of it as a solved problem. And then you can do things like policy gradient. Haven't done it, but it'll be interesting. There's old work from the old neural networks control, which are called SNAP, single network adaptive grading, that kind of does it. And finally, imitation learning. So these trajectories could be used to train policies and values. I have a really fast ML multi-layer perceptron CPU site. Funny thing happened last summer. I decided to write my neural network module. I haven't trained a neural network in like 20 years. So I wrote one, and it's kind of okay. Then I decided to optimize the matrix multiplication. Spent 3 days optimizing it. Ended up being 2 times faster than OpenBlast and Intel MKL, which is the industry standard. As a result of that, my multi-layer perceptron on the CPU runs 2 times faster than PyTorch on the CPU. So now I have a very nice little neural network package, probably useful beyond optical. So if you have a bioptical license, you'll be able to code it. But of course, when you go to bigger things, that's not the case. So what's outside the scope of optical learning from large data sets, all you put down on GPU? Oh, vision processing is vanished. Optical expects inputs that are features of the states and controls, i.e. some kind of virtual sense. Why? Because it needs to have a generative model of whatever you're providing. So what you should do if you, let's say you have a camera pointing at the world, download one of the models that can do vision processing and pull out virtual markers or virtual poses, whatever, and that's the thing that feeds into optical. And finally, brute force reinforcement learning sampling. So here's a fun fact that most people don't realize. CPUs are not slower than GPUs for physics simulation. I mean, I found that myself 10 years ago when I tried to port MuJoCo to both CUDA and OpenCL, and I tried it on both NVIDIA and AMD cards, and turned out when the processors are matched, they're the same. Today, if you compare the big, nice Threadripper 96 core to RTX 5090, they have the same number of transistors, about 95 billion. They have similar power consumptions. They have very similar throughput when they're fully loaded, 35 million steps per second. The advantage of GPUs right now is NVIDIA managed to sell a lot of them. And so people just have them. And for that, use NJLab. It's really nice software out. It's kind of complementary to what I'm doing. I don't want to compete with those guys, especially since they get paid very generously from Google, and I haven't been paid in long. I'll stay away from them. Thank you.